Welcome to the session of magnetic inductance and magnetic energy. These are two different topics, syllabus point of view, but conceptually they are interrelated. Hence, we have inductance, which is a magnetic phenomenon, magnetic inductance, and a quantity, which we say energy, which is magnetic energy, we are going to discuss. Because we are in unit 2, which is magnetostatics. When I say inductance, it is magnetic inductance. When I say energy, it is magnetic energy. The first one is self-explanatory. Inductance means by default it's a magnetic phenomenon. Like we say capacitance as electric capacitance, we say inductance as magnetic inductance. There is no confusion in that. But energy means there can be two types of energies, electric energy and magnetic energy. In first chapter, that is in electrostatics, we have seen electric energy. In the second chapter, we are going to discuss now energy, which is magnetic energy. Here they are categorical. Now coming to the inductance. In first unit, we discussed electric capacitance. In second unit, we are discussing magnetic inductance. So needless to say, inductance means it's magnetic thing. But here if you observe, I have written inductances, plurality. Means there will be more than one type of inductance. Of course, as you can see here on the screen, the first one is known as the self-inductance and the second one is known as the mutual inductance. Now it comes like this. A current carrying conductor is surrounded by magnetic field. Magnetic field is induced in the vicinity of a conductor which is carrying current. Now what will happen is the produced magnetic field will also link to the conductor through which the current is flowing. This is called as self-inductance. The magnetic field is getting induced into the cable and the conductor from which it has been produced. Now, if suppose the magnetic field is produced by one conductor due to the flow of current, the produced magnetic field is getting linking to the adjacent conductor, some other conductor which is in the vicinity, and vice versa. That means that other conductor is also producing some magnetic field. That magnetic field is getting induced in this first conductor. This happens mutually on either sides. So we say this as the mutual inductance. As a layman way of understanding, I have just told you what is self and what is mutual. Now let us try to understand these a more technical and more elaborate way. As you can see here, the amount of flux that is linking to the conductor will be more if you increase the turns in the conductor. First of all, you have to make the conductor in the form of a coil by making turns. If the number of turns are more, then more amount of flux will be, magnetic field will be induced in that coil. Alternatively, I use the terms magnetic field and magnetic flux because magnetic field cannot be visually seen with our eyes. However, it can be represented in the form of magnetic lines of force. That magnetic lines of force, bunch of lines of force, we say as magnetic flux. So don't get confused when I use the terms alternatively, magnetic field and magnetic flux. Magnetic flux is a form of representing the magnetic field. Magnetic field is one which cannot be visually seen but can be experienced. Okay. So now, here we have in red color, I have used a conductor which is in the form of a coil. Let us say the number of turns are capital N and I have used phi. Phi is the magnetic flux which is equivalent to the magnetic field that is being produced. Now this is due to the current I that is flowing in this, because if there is no flow of current, there won't be any magnetic field produced. If there is no magnetic field produced, there is no question of the amount of magnetic field that is linking to the conductor. All this does not exist. So first, just presence of the coil is not sufficient. Current I has to flow in that. As a result of flow of current, there results a magnetic field. That magnetic field we represent in the form of imaginary lines of force. That's why I have used dotted lines here. Imaginary lines of force, which we say as magnetic flux. And the amount of magnetic flux that is linking to the conductor, it depends on the number of turns in the conductor, which we say N, capital N. So I think you understand. I, phi, N. I is the source, because if there is no flow of current, there is no magnetic field. If there is magnetic flux phi, then if the number of turns are more, then more amount of flux will be linking to the coil. Now, L stands for the self inductance, M stands for the mutual inductance. I have written two M's. Reason? Mutual inductance between first coil and the second coil, and vice versa, mutual inductance between the second coil and the first coil. As I told you, if the magnetic field that is produced in the first coil is linking to the second coil, the magnetic field produced in the second coil can also link to the first coil. This is two-way. That's why we say mutual. Of course, we are dealing inductance, but it happens in a mutual manner. So we say mutual inductance. That's why we have two M's. M21, M12. But whereas L, it is only one. Now, what is L equal to? Basically, magnetic inductance is a ratio. You have a numerator, you have a denominator. It's a ratio. Ratio of what? The total flux that is linking to the coil. Why I am saying total flux linking to the coil? Because phi is the flux that is produced. N phi is the total flux that is linking to the coil. The amount of flux may be 10 Webers. But how much it links to the coil depends on the number of turns of the coil. That's why we say total flux. N phi is total flux linking to the coil by the current that is producing the flux. I is, after all, I is result due to I is the source for producing the magnetic field. If there is no I, there is no current flow, there won't be any magnetic flux. So, the self inductance is defined as the ratio of total flux linkage to the coil to the current that is producing that flux, N phi by I. Similarly, if you come this other way, you have two coils, N1 number of turns in the first coil, N2 number of turns in the second coil. I1 is the current flowing in the first coil, I2 is the current flowing in the second coil. Now, there are two types of fluxes. Flux produced by the first coil linking to the second coil. Flux produced by the second coil linking to the first coil. Here you can see phi 12. Phi 12 means flux produced by the first coil linking to the second coil. Here you have phi 21. Flux produced by the second coil linking to the first coil. These are fluxes between the two coils. However, you have self inductances. Flux produced by the first coil linked to first coil, we say it as phi 11. Flux produced by the second coil linked to second coil, phi 22. This will be there anyhow, but that is not the question. We are in the purview of mutual inductances. Mutual means between second and one, between first and second. That's why I am not writing these two. Now, M21 is N2 multiplied by phi 21. What does it mean? The total flux linking to the second coil. Numerator has the total flux linking to the second coil. How much flux linking to the second coil? Depends on the number of turns of the second coil, N2, and phi 21 flux linking to the second coil due to the flux linking to the second coil due to the first coil. Next, M12. In place of N2, you have N1. In place of phi 21, you have phi 12. Flux linking to the first coil, number of turns of the first coil, flux linking to the first coil due to the second coil, phi 12. First flux linking to the first coil due to the second coil, phi 12. How much flux linked to the first coil? N1. So, just the difference is in place of N2 you have N1, in place of phi 21 you have phi 12. After all, why do you get flux in the first coil? Because of current in the first coil, I1. Here I2, in place of I1 you get I2. So, just these are the two different types of mutual inductances between first coil and second coil. Next, we have an associated topic which is called as magnetic energy. I am saying inductance and energy because inductance is magnetic phenomenon, magnetic inductance and magnetic energy. Then, while discussing the inductances and inductors, I mean to say that inductance is a phenomenon exhibited by a device known as inductor. Capacitance is a property which is exhibited by a device known as capacitor. So, I can say inductance is a property of inductor, capacitance is a property of capacitor. Now, what is a capacitor? it's an energy storage device. What kind of energy? Electrical energy. Now we are in magnetic domain. We are in unit 2, magnetostatics. Now, what is inductance? It's a property of inductor. What is inductor? It's a device which stores energy. In which form it stores energy? In the form of magnetic field. That's why we say inductor is a device which stores energy in the form of magnetic field. Got it? So ultimately where we are coming to? Energy. Inductance is a property of inductor. Inductor is a device which stores energy in the form of magnetic field. So underline the fact, energy. So inductance, property and energy are associated. That's why we have the topic magnetic energy. Now, in the first unit we have seen electric energy. Here we have magnetic energy. Whether it is magnetic energy or electric energy, the unit will be same. Joules. And you observe the unit of work done and unit of energy will be same, joules. What is the reason? And even in this expression, if you observe carefully, I am saying energy, but I am writing here W. Of course, M stands for magnetic energy, because in first unit you have electric energy. There we have written WE. E stands for electric. Here M stands for magnetic. That's a different thing. That is a subscript. Now W, I am writing this W because work done unit is joules, energy unit is also joules. How they are connected? Let us go back to our school days, where you have seen for the first time what is work, what is energy. See, work is done with the expenditure of the energy. See, if you want to do some work, you have to burn some calories. You have to use your energy. You are expending the energy, expenditure of energy. So, you are doing some work by burning the calories in your body, isn't it? That's why you need some energy to do some work. So, they are almost interconnected. More the work that you perform, more the work that you do, higher will be energy that is burned. Higher the energy that you are burning, it correlates to work done. So there is an interdependent intricacy here. These two are not independent, they are interdependent. So here Wm stands for the work done in the presence of magnetic field. So these two are associated quantities. Suppose you have an electric field due to an electric charge. If I want to move another charge in the presence of electric field, then you have to make some expenditure of the electric energy. Same thing in the case of magnetic field. If you want to move a magnetic charge in the presence of magnetic field, then you have to make some expenditure of energy. Of course, either along the direction or opposite direction, that's a different thing. That depends on the polarity, but work has to be done. So now, as we have in first unit, 3 ways of representing electric energy. Here we have 3 ways of representing magnetic energy. 3 alternate ways, I can say. You did not use all 3 ways. Any one of the 3 ways you can use, but 3 possibilities are there. Now, our subject is electromagnetic fields and transmission lines. Electromagnetic fields. It comes under field theory. But this electric energy and magnetic energy is not for the first time you are listening in your life, isn't it? You have already seen in your school days and college days about this electric energy and magnetic energy, because you have electricity and magnetism in your school days also. Now, we have also studied some circuit subjects. Before coming to the subject, we have also studied some circuit subjects. Now, what is the formula for electric energy? Half CV square. What is the formula for magnetic energy? Half Li square. These were the formulas that you have been using in circuit subjects, networks. Capacitance, voltage. Inductance, current. CV square, Li square. Half, both are same. These are the formulae which are applicable in circuit theory, where C stands for capacitance of the capacitor, voltage applied across the capacitor. L stands for inductance of the inductor, I stands for current flowing through the inductor. Where do you have these inductors and flow of current? In circuits. Now, where we are not in circuit theory, we are in field theory. So now, half Li square. In field theory, you don't have inductor, but you have inductance property. Inductance property in the medium, because fields propagate in this medium, you have inductance property. By virtue of what? By virtue of mu, magnetic permeability of the medium. That's what I am saying here. You do not have inductors in the field, in field theory, explicit inductors, but you have magnetic inductance property, magnetic property, which is similar to inductance in field theory, that is mu. That's why we say magnetic permeability of the medium. You don't have capacitors. You have capacitors in circuit theory. You don't have capacitors in field theory, explicit capacitors. But that capacitance nature is exhibited. It correlates to epsilon. That's why we say electric permittivity. So now half Li square, in place of L you take mu, half as it is. I, we don't have current. Current means amperes. In field theory you have amperes per meter. What is it called? Amperes per meter. Magnetic field. So H square. In place of half Li square, which is in circuit theory, in field theory you have half mu H square. That's what I have written here. Half mu H square. But of course magnetic field is a vector H bar. Why I am writing H square here? Because H bar dot H bar, the dot product of two vectors will be scalar. So H square, directly I am writing H square. Don't get confused. Two identical vectors, I am writing directly here H square. Half is constant, so I am taking out of the integral. But why I am taking integral? Because if you take this quantity, you get energy density, not energy. But if you want energy pertaining to a unit volume, at certain volume, then you have to integrate this. Half is anyhow outside. You have to integrate this throughout the volume. Then you get energy. You know, power is obtained by integrating power spectral density. Charge is obtained by integrating charge density. Flux is obtained by integrating flux density. Energy is obtained by integrating energy density. So if this is energy density, the integral of this will be energy density. That's it. Simple and straightforward. Now, two alternate forms. We know that B equal to mu H. This is called constitutive relationship in electromagnetics. One of the constitutive relationships. Now, in place of H can be written as H equal to B by mu. B bar by mu. In place of H square, you can write B square mu. Already one mu is there, mu. So what do you get here? Because H square you have B square by mu square. Then if you substitute, what do you get here? This mu square cancels, B square by mu. B square by mu, half will be as it is there. This is one form. Next, then another form, B bar dot H. This is also same as this. How? Let us see. What do you have here? B. B equal to mu H bar. Next, you have H bar. H bar. What is this? Mu H bar dot H bar. H square. Mu H square. That's what you have here. So essentially, these are the three different ways of representing energy, magnetic energy, which is expressed in joules. Of course, whether it is electric energy and magnetic energy, it is in joules. If you remove this integral, what do you get? Energy density. If you remove this integral, the rest of the thing, half B square by mu, half mu H square, that is called as energy density. Energy per unit volume. Then we have joules per cubic meter, because unit volume means in meter kilogram second. System of international, we say cubic meter. Joule per cubic meter. If you don't have integral, use joules per cubic meter. If you have integral, that is called energy, not energy density. Then you have only joules, magnetic energy. So this concludes inductances, namely self-inductance and mutual inductance, and magnetic energy, which is expressed, which is having a unit of joule and which is expressed in three different forms.